physics. Now let's talk about refraction. So for today, what I want you to think about is, have you ever been looking at some glass and all of a sudden light hit it a certain way and you see this spray of color of light? Well, what's happening there is light is being bent, and as it's being bent, it's going to come off at different angles. And that's a thing called dispersion. So dispersion is this thing where you bend light and it will, because of the different wavelengths of light, the different colors of light, frequencies if you will, that'll cause it to spread that light out. And then you get white light to colorful light. And that's what refraction is going to be. Refraction is going to be this bending of light. So if you will take a moment just to jot that down, that refraction is bending light. Remember, we just talked about reflection, and reflection is that bouncing off of light, where here refraction is going to be that bending of light as it passes through another transparent material. That's very important. Now let's see what happens to light as it's bent when it enters a new medium. So let me take a look at this. Notice we have an incident ray, and notice that weak reflected ray. If we were to measure the angle from the midline to this weak reflected ray, you would note that the reflected ray would match the angle of incidence. But that doesn't happen whenever we have light entering a new medium and passing through. Light's going to be bent. It's going to do one of two things. It's either going to speed up or slow down. And so if it bends towards this normal line, then it's going to be slowing down. If it bends away from the normal line, then it'll be speeding up. So we know that this guy is slowing down, and to figure out, there is a specific relationship called Snell's Law that helps us figure out what this angle would be. We're going to take a look at that, but I just wanted to take a moment so we see that bending happen, and now we'll move on from there. The relationship at which light will bend as it enters a new medium is based upon Snell's law. And this is what Snell found, that whenever you take the index of refraction and times by the sine of the incident angle, so the angle going in, and that index of refraction is for that material that it's currently in, and we'll talk about what that means in just a second. If you take those two values and multiply them, it's equal to the index of refraction in the new medium times the sine of the new angle, because remember, it's going to bend either towards the normal line or away from the normal line. And so those index of refractions are just the relationship of the speed of light within that medium compared to the speed of light in a vacuum, which is 3 times 10 to the 8th. So this value here for C, you see right here, C is going to be 3 times 10 to the 8th. And then this velocity is going to be whatever the speed of light is in that new transparent medium. So that's what that index of refraction stands for. N1 and all of the ones on the one side of the equation is the incident side, or where it's starting, and then the 2's are going to be on the refracted side, or where it's going into. So if we did an example problem, this is what it would look like. You've got all this information at the top, but then it tells you that the index of refraction for the glass, so that's index of refraction of the new medium, not the angle of, not the index of refraction for the incident medium. So we're looking at NR, if you will, as 1.6. And now you see the angle there. That's the angle of incidence. We would put that at theta I. And you've got theta Ni is going to be 1 because it's coming from air. So air is always 1. So we have 1 times the sine of 35. We're going to divide by that 1.6 and then multiply by the inverse sine to cancel out the sine. So we get theta R by itself, and it'll be 20 degrees, or 20.2 degrees. One thing you should note, that it moved from 30 to 20, so it got closer to the normal line, which means it's slowing down. Now let's take a look at this simulation here. I'm going to shine a light down here, and we're going to put it at 10 degrees. The first thing I want you to recognize is the law of reflection taking place. So you have the angle of incidence. This is our normal line, and here is our mirrored surface, or our flat surface in this case, and we have a reflected ray, even though it's very weak, going off, and you'll notice the angle of incidence is 10 and the angle of reflection is 10. Pretty neat there that it still applies on flat surfaces, even like water. The next thing we would look at is this light is actually also bending as it goes in. And notice it's bending towards the normal line. I put it at 10, and the index of refraction, I'm sorry, the angle of refraction is less than 10. And so we see that it bent towards the normal line. That means that it's slowing down. If you look over here, the index of refraction of water is 1.3. That means it's going slower in water than it would in air. Now watch what happens whenever I switch these two. It bent away from the normal. So we did this thing where we're coming out of a slower medium to a faster medium. It sped up and it bent away from the normal. So that's what I wanted you to check out with this simulation. And hopefully that makes you have a little bit better understanding of. Thank you for watching About Refraction today. If you have any questions, please reach out.